Okay, hello everyone. Welcome to 130B, Quantum Mechanics. Today we are going to continue our discussion of perturbation theory. So last time we have started talking about time-independent perturbation, and also it is in the case where there's no degeneracy in energy levels. And here is the summary of last time's result. So essentially, in perturbation theory, for time-independent perturbation, we want to start from a Hamiltonian H0, whose spectrum we fully know, which means we know its eigenvalues and its eigenvectors, all the energy levels, and the corresponding states. We also know what is this perturbation, and this perturbation will be a matrix basically represented in the eigen basis of H0. So suppose we know the matrix element in this perturbation, and the perturbation, of course, is supposed to be small, and suppose we also know what are the energy eigenvalues and the corresponding eigenvector basis, we can use it to reconstruct the perturbed energy and the perturbed corresponding eigenstates. For the new Hamiltonian will be basically, the new Hamiltonian will be H0 plus V, basically. And then that's the conclusion. And then in many cases, the expression can grow very complicated very quickly. But the essential idea of perturbation theory is Taylor expansion. All we have been doing is Taylor expand the energy eigenvalues and eigenstates. And usually in Taylor expansion, the important thing is to compute the derivative of the function with respect to the variable to any higher order, and then plug into the Taylor expansion formula. So perturbation theory essentially is a tool that allows us to calculate all these derivatives iteratively, and then without knowing the function itself. So this idea is actually very similar to what is happening in deep learning nowadays. Like in deep learning algorithm, we basically want to build a model to fit the data maybe, and then you want to compare your model prediction with the data and then construct a loss function, which you try to minimize by tuning the model parameter. And the way that people do this minimization is to compute the loss function, starting from some model parameter, compute the loss function. But then, if you want to know along which direction I should optimize my parameter, you need to compute the gradient of your loss function with respect to the parameter, right? And then this is very difficult if you think about it. If you know what is the loss function, as an explicit function in terms of the parameter, then you can use calculus to do this computation of derivative. But in deep learning, the model is so complicated, you can't write down any meaningful analytic expression. So how do people do that? People use this kind of strategy, perturbation theory. It's like as long as you can calculate this function in the forward direction, you can backpropagate the gradient. You can basically evaluate the gradient. Just by knowing the function, how does the function evaluate at that single point? You know its gradient, basically. So that's the idea. So here you can think that this V is kind of like a perturbation adding to the H0. It's like a perturbation of your parameter, and then you try to compute the gradient of your function with respect to parameter, and then this is basically the gradient backpropagate formula for this case. Okay, so that's just a side comment, and then and because nowadays deep learning is so popular that people has already basically hard-coded this formula in all the deep learning package. So nowadays, actually, you don't need to learn this. You just need to know how to use backpropagation in deep learning. You can compute all these gradients of eigenvalues and eigenvectors. But apart from this math, let's build some physical intuition. What we are doing is like this. So we start from H0, which is diagonal, and it's diagonal meaning that it has zero matrix element everywhere, and only on the diagonal it has matrix element like En and Em, which correspond to the energy eigenvalues. And then we are going to modify this H0 by some perturbation V. And by saying that V is a perturbation, we mean that every matrix element in this V are small. So this matrix is the full matrix after we apply the perturbation to the original Hamiltonian in the Hamiltonians in this original Hamiltonian's eigenbasis. So it looks like that. So if you look at this matrix, the matrix will be dominated by the diagonal part because diagonal element, this EM and EN and EM, they are much larger. They are much larger than all these V's. All these V's are just very small numbers. So you can think of it, it's a matrix that is almost diagonal, but there's only some off-diagonal matrix element which is quite small compared to the diagonal matrix element. So the goal is to re-diagonalize this almost diagonal matrix, which is this new Hamiltonian. So we can see this problem is simpler than I just give you a random matrix and ask you to diagonalize. Because in that case, you have a lot of very big off-diagonal matrix element of at least of the same order as the diagonal. So the hope is that if the matrix is already very close to diagonal, then the re-diagonalization should only require a smaller effort, actually. So that's why the new eigenenergies and eigenstate can be obtained perturbatively by perturbative corrections based on the original eigenvalue and eigenstate of the Hamiltonian. Because you are only changing this Hamiltonian by small amount, then the eigenvalue, eigenstate will also change by small amount. And then if you look at this Hamiltonian to the first order, you can say, okay, then since it's almost diagonal, let's just ignore all these off-diagonal matrix elements and as if they don't exist. Let's look at the diagonal. The diagonal matrix element goes like En times plus Vnn. I can just treat that as my new eigenvalue because if I'm blinded to all these off-diagonal matrix elements, this is just another diagonal matrix. So that is indeed the case. If you simply go to a matrix, write down this perturbed matrix, and then read out the diagonal matrix element, the diagonal matrix element is the first order to the first order correction of the eigenenergy. So that's why the eigenenergy to the first order, the eigenenergy correction is simply the diagonal matrix element, which is also just to re-evaluate the energy expectation value on the old eigenstate. So this n is an eigenstate of H0, but n is not the eigenstate of the perturbed Hamiltonian H. But nevertheless, you can just take your perturbed Hamiltonian and evaluate its energy expectation value on the original state. And that gives you what should be the new energy level in this case. So that is the physical meaning of the first order correction to the energy. And what about the correction to the state? Why does the state being correct in this way? For example, you have an n state. And then, so the first order correction to the state basically corresponds to a process called hybridization, or hybridize, or mix the original state with another state that are connected to the original state by the non-vanishing VMN. Because if this VMM is a mth row, nth column of diagonal matrix element, if there is not such a matrix element, that means suppose all these off-diagonal matrix elements are exactly zero, if they are exactly zero, then you don't need to do any correction to the eigenbasis, right? The matrix just the diagonal being modified by a little bit, and then it is still diagonal. It is the original basis is still a good basis, where the new matrix is actually already the old basis is already an eigenbasis of the new matrix. Is all the off-diagonal matrix elements are vanishing, but they are not. They are small, but not zero. So that's why you need to correct. And the amount of correction you have to do necessarily will be proportional to the non-zero matrix element that connects M and N. So that's the idea. The hybridization coefficient actually is, first of all, proportional to the transition rate. This VMN actually describes a rate that your old state can transition to a new state connected or given by this Hamiltonian. So you can imagine that there is an old state. There are two levels in the, and then the two levels correspond to En and Em, and they have two corresponding old eigenstates. And then there's a matrix element. The perturbation is providing a very weak matrix element connect these two states. And then if there is such a connection, then the new state will partially be basically added to the old state in order to correct that. And the correction not only is proportional to this connection, but it is also inversely proportional to the energy level spacing. Meaning that if the two spaces are far apart in energy, for example, one is very high in energy, one is very low in energy, then even though there's a connection between them, they don't talk to each other typically. It is just a separation of energy scales, which is pretty intuitive actually in our daily life. Like when we're talking about chemical reaction, we don't need to care about nuclear physics, right? This is because nuclear physics is happening at a much higher energy scale, which even though there may be some process which couples the electron to the nucleus, and then we can't say that this kind of process, the coupling between a chemical reaction and nuclear reaction, we can't say they don't exist, but it is just because these two processes are very different in energy scales. So in this way, they are isolated. So, I mean, they don't affect each other too much. And then only those levels which are already very close to each other, then this perturbation will make a big difference, because originally if the level spacing is small, then adding this perturbation, if this perturbation is even larger than the level spacing, then you can see this coefficient is no longer a small quantity. So that is where the perturbation is not quite reliable in that case. So we always need to assume that there's a difference between these energy levels, and then that's the region we can reliably apply this perturbation theory. Okay, so that is this formula about state correction. And we can see from this formula, when the levels are very close to each other, the hybridization coefficient will diverge, which signifies the breakdown of a non-degenerate perturbation theory. And then this phenomenon is also called the level resonance. If two levels are too close to each other, then they are too sensitive to perturbation. And in that case, any weak perturbation that connects these two levels can create a level resonance. So we will be talking about what we should do when these two levels are too close to each other. Then that's the next topic about degenerate perturbation. And then there's another effect called the level repulsion. Level repulsion corresponds to the second order energy correction. And if you look at the energy correction at the second order, this is the formula. And this formula basically says that the energy level always try to repel each other. So previously, we say that if you have two energy levels, the first order correction is simply just add to this energy level by VNN, which is like energy level will be directly addressed by this perturbation. But there is also a second order effect, which means that, for example, this energy level En, it will actually experience the effect from Em by basically first perturb the state to M and then perturb it back. So that's how you read this formula. This formula means that you start from the N state, you use a VNM matrix element to connect the N state to M state, right? Because VMN describes the transition from N state to M state. And then VNM describes the transition backwards. So the reason that you have this factor on the numerator is because you need to go from the N state to M state and then going back. And by doing this second order process, you will accumulate these two transition rates. And then this is not the only factor. There's also a denominator, which is set by the level spacing. And you can see in this case, when this VMN norm square, this numerator is always positive. But the denominator can be either positive or negative depending on whether n is greater than m or smaller than m. So let's assume that En is smaller than Em, which is the case that I draw in this picture. Then you can see that this one is smaller than that one, then the whole thing is basically negative. So if you want to compute what is the correction received by the En level, you will see that after correction, this energy will be less than En, meaning that the level was originally here, but after the second order correction, it will go to more negative levels, basically be pushed down. And then if you consider the other case where En is greater than Em, and the level will be pushed up. So that means if somehow the system only has these two levels and has a perturbation connecting them, then what happens after perturbation is the lower level becomes even lower and the higher level becomes even higher. This is like you are visiting your friend's home, and then your friend is a rich guy. So you go to your friend's house and come back to your home, you feel that you are poorer. And then if your rich friend come to your home and see, oh, how poor you are. And then when he come or she go back to their own house, and then they think, oh, I'm really a rich guy, I'm richer. So this perturbation effect is like the poorer people feel they are even poorer, and then richer people feel they are even richer by talking to each other. So this perturbation establish a connection between different levels, and the different levels always want to repel each other. So this is the second order effect. So this effect helps us to memorize, because it's really difficult to memorize whether the denominator is n minus m or m minus n. It's easy to understand that the numerator, because it involves a second order process, you need to go there and come back. But what about the denominator? And this story that I just told is a way to memorize this effect that the level always want to repel. Okay, such that you don't get this sign wrong, basically. So let's apply this kind of idea to a very simple case, which we start from the beginning. We say that we have a qubit system which has a dominant diagonal sigma z, a Pauli z matrix, which is this H0, and V correspond to lambda times sigma x, which is this off-diagonal. So indeed, this creates a case where we start from two energy levels, one at energy 1, the other at energy minus 1, and connect them by this perturbation. So this unperturbed spectrum is like there's a state 0 correspond to +1 energy, and then state 1 correspond to -1 energy. So using the perturbation theory, we just plug everything into the formula. We can see, for example, the state perturbation. The new 0 state will be connected to the original old 0 state by this effect, because 0 now can go through the perturbation and talk to state 1. So the new 0 state will not only contain the leading 0 component, it will also contain a fraction of component that is coming from state 1. And then that fraction will, of course, be proportional to the strength that the 0 state can be connected to one state, which is described by this off-diagonal matrix element, and in this case, it's lambda. And then we also need to take care of the denominator. The denominator will be set by the energy difference, and in this case, the energy difference is 2. So that's why the correction is like that. And then for state 1, it will also receive a correction, and then that goes like that. So that's the idea. And then if you try to say, okay, the original 0 and 1 state, they are orthogonal to each other. So after the correction, we have a new 0 state and a new new state 1, right? Are they still orthogonal to each other? Even though you can see 0 gets, this can be visualized in this way. You can think this is the 0 state, this is the 1 state. Originally, 0 is a unit vector along this direction, and 1 is a unit vector along that direction. So after correction, 0 goes to 0 plus something along the 1 direction. So it basically goes to here, and then this amount of change is basically this lambda over 2 times 1, right? So you go to the new 0 prime state. So this is the 0 prime state. And then you can see very nicely, 1 also goes to 1 minus. So it goes in this direction, minus lambda over 2, 0. And then it goes to a new state, which is this 1 prime. So you start from 0, correct it to 0 prime by going along the 1 direction. But if you start from 1, go to 1 prime, going along the negative 0 direction. Why do we need to do that? In order to preserve the orthogonality, right? So that is the only way that you can see these signs are also correct, because when you do this calculation, although the matrix element, they are the same, but the denominator basically flip their E0 and E1, and that leads to a relative sign difference between these two corrections, and that makes a lot of sense because otherwise, after the correction, your state will not be orthogonal to each other. But and very fortunately, that doesn't happen, so perturbation theory makes a lot of sense in this state, state hybridization. And then there's also energy repulsion effect. So in this case, there's no perturbation that is directly applied to the diagonal. So there's actually no first order energy correction effect. There's only a second order energy correction, and the second order energy correction is, as we said, at level repulsion. You need to go through the from one level, go to the other level, and coming back. If you are a higher level, your energy will be even higher. If you are a lower level, your energy will be even lower. So they repel each other, and then that's the result. So if you try to compare this result with what we said at the very beginning, you will be able to find that they exactly matches what we obtain from this exact solution. Remember, we have solved this problem at the very beginning of several lectures ago, and then we found some exact solution, and then for that solution, we just apply the Taylor expansion formula very brute forcefully, and then we obtain these results. For example, these are the energy corrections, and these are the state corrections. Although we're not able to compute higher order in this case, because you know that the higher order formula would be too complicated, I don't want to present it, but at least you can see to the leading order, which is in most cases is sufficient, and then they all matches the Taylor expansion result of this exact calculation. Okay, so that justifies that this perturbation theory is indeed working. Okay, so that is how we apply this non-degenerate perturbation theory. Any questions? Yeah, that's very good. So, so let's move on to degenerate perturbation theory. So the previous non-degenerate perturbation theory has a big problem because you can see this energy denominator everywhere. Both in the state correction and in the energy level correction, you always have something like En minus Em, and which is very nasty because when N and M are two levels that are too close to each other, everything basically breaks down. All these terms are going to diverge. So how do we deal with the case where there are degeneracies in this H0 spectrum? Because sometimes you can't avoid that your original Hamiltonian already have two levels which has exactly the same energy. Then if you label these two levels by N and M, then En minus Em is going to infinity, for example. So the idea there, the strategy here is called divide and conquer. What does it mean? For example, I'm drawing this picture. This picture is supposed to represent the matrix. So I'm using this color to represent matrix element. So every little square in this big square is like a matrix element in a square matrix. And white color indicates it's a 0. And blue color, green color means that it's a, let's say, negative number, and red is a positive number, and other color basically is imaginary or complex numbers, basically. So just don't worry about that. And then suppose this is my H0, and then you can see H0 is diagonal, first of all, and then its diagonal matrix elements are real numbers, which means it's only positive or negative. Other than these off-diagonal matrix elements, sometimes they can be a generic complex number. This color is supposed to indicate the phase that goes from red to yellow to green to blue to red, something like that, as you circle around the complex plane. But anyway, so this will be the perturbation that I want to apply to this system. So the system, unfortunately, now have degenerate levels. For example, these two levels, they are degenerate, and these three levels, they are also degenerate because they have exactly the same strength on the diagonal. So instead of trying to say, okay, how do I do energy correction for every level, because it's no longer possible to apply the formula, we want to ask, how do I do perturbation at least to these two subspaces? So the degenerate perturbation theory is not considering each level individually, but the first step is trying to group the level which is of the same energy into a subspace. For example, the first two states, they have exactly the same energy. They are grouping into the so-called low energy subspace because their energy is actually lower. The green color indicates it's a negative energy. And then the remaining three states, they group into the high energy subspace. And then instead of trying to ask, how do we correct every energy level or every state, we ask, how do we correct every subspace? So it is a collective correction. It is no longer it is no longer correct the single energy level. It's trying to correct effective Hamiltonian in this subspace. So you can see for a single state, you can just use a single energy eigenvalue to label the energy of that state. But now if you have two states which is degenerate in a subspace, then in order to describe the energy or the physics within that subspace, you cannot just use a single number. You cannot also use only these two numbers on the diagonal. You actually need to use this 2 by 2 matrix as a local Hamiltonian to describe the energy, because already you have more than one state in your Hilbert space, then your energy operator will be a Hamiltonian operator. So that's the same idea for this one. So the idea is that you first add this matrix perturbation to the matrix, which looks very complicated like that. And then you try to apply some perturbation theory method to remove the so-called off-diagonal blocks. So we can now block this matrix into diagonal blocks, which correspond to these 2 by 2 and 3 by 3. And there's also off-diagonal. Now it's not off-diagonal matrix element, but off-diagonal block, which correspond to this 2 by 3 block and 3 by 2 block. You can see that the first step is to clear up this block by perturbation theory to remove this matrix element, so-called block diagonalization. So you first diagonalize the matrix, but not diagonalize immediately to this diagonal, but diagonalize into these two blocks. Then within each block, you can further apply perturbation theory and then to remove this off-diagonal. Because after you clear up this off-diagonal block, there will be corrections applied to these energy levels. So although these energy levels are degenerate at the beginning, but after this block diagonalization, you can see there's a very slight color difference between this blue, green, or red. Actually, it's not very visible, but doing this will create some splitting between the energy level, which then allows you to do another perturbation theory within each block separately, and then eventually diagonalize the whole matrix. So that's the idea. So the idea is to divide and conquer. So so first divide into subspaces, and then first clear up the off-diagonal block, and then go to each block and further divide and conquer, divide and conquer. If there's still degeneracy, for example, within this block, you still need to divide it and then try to conquer. So that's the idea, okay? So the degenerate perturbation theory is trying to explain how to do this middle step, because that's the most important step. Once we know how to clear up this off-diagonal matrix element in the off-diagonal block, we can just keep applying the same algorithm until we finally diagonalize the whole matrix. So, so that's what we want to explain in this degenerate perturbation. Okay, the big strategy is clear. So, so here are what I have been talking about. Let's go through it very quickly. That there's some degenerate state that spans a Hilbert space called the degenerate subspace. And the first is to apply non-degenerate perturbation theory to block diagonalize and to convert everything into these diagonal blocks. And within each diagonal blocks, there will be an effective Hamiltonian, and then we can continue to do this diagonalization continuously. So, so for this effective Hamiltonian, if the degeneracy has been completely lifted, then we can proceed with non-degenerate perturbation. If it is not fully lifted, then we can again divide and then move on. Or maybe we can proceed to so-called exact diagonalization, which is not using perturbation theory. It's no longer a perturbative approach, but you can just plug this smaller matrix into Mathematica and try to diagonalize it. But that will be much easier than diagonalizing a large matrix. So that's another idea. Okay. Okay. So in order to explain how to do this, we need to first set the stage up. The first thing to do is to generalize the Hermann-Feynman theorem to this case where we have degeneracies. Because Hermann-Feynman theorem, as we learned previously, is the very essential key theorems in perturbation theory. But for these degeneracies, basically that means there will be multiple levels of the same energy. So that's why instead of using a single integer to label every state in our unperturbed Hamiltonian, we need to use two integers. The first integer n is called the principal quantum number, which only labels the degenerate subspace. So every state within the degenerate subspace will have identical energy. So energy will only depend on this principal quantum number, and then any alpha, which is called the secondary quantum number, labels the remaining orthogonal degenerate state within each subspace. So no matter what alpha is, as long as you are indexed by the same n, you have exactly the same energy, E of n. So E only depends on n. But alpha is also important because within that subspace labeled by n, you still have many degenerate states. Those states are not the same. They have the same energy, but they are not the same state vector. They are actually orthogonal to each other. So that's why we still need a secondary quantum number to label those degenerate states. And in that case, the original Hamiltonian H0 has an eigenequation that looks like this. Okay? So, so for these states, they also form an orthogonal basis, meaning that if you have an n beta state and m alpha state, and then if and only if n equals m and beta equals alpha, that these two states are labeling the two integers are labeling the same state. So otherwise, they are orthogonal, meaning that their scalar product will be 0 as long as either m doesn't equal to n or beta doesn't equal to alpha. So these two delta symbols basically are multiplied together. So the first delta symbol is trying to check whether m equals to n, and only in that case it's 1. And then the second delta symbol is to check whether alpha equals beta, and only in that case, when alpha equals beta, it's 1. So in order for these two delta symbols multiply to 1, you need to simultaneously satisfy the condition that n equals m and beta equals alpha. Okay, so that is the orthogonal condition. And then for the perturbation that we apply to the system, it's just write down the matrix element. So this is what we know, because if someone needs to describe what is the perturbation to you, they actually need to tell you how does the perturbation connect every level to every other levels. So for every level n beta, there will be a matrix element that connects it to another level m alpha. This connection can happen either within the same block or between the block. But our first priority is to first clear up all those matrix elements that is between the block. So that's the idea. So now we will move on with this standard setup, and then this V will times a small quantity lambda and add to 0 that creates our perturbed Hamiltonian. And our goal, of course, is to find the new eigenvalue and eigenstate. So the new eigenstate will be labeled by n beta, but actually not quite the eigenvalue in this case, because as we said, we are not dealing with each level individually. So now the energy is no longer described by a single value, but you can see this is described by another matrix. So this is called the block diagonal. This is the effective Hamiltonian within that n block. So this is the perturbed Hamiltonian when it acts on a state which is within the block n. Then not only that state can be previously, if it is an eigenstate, right, then it will just be the state times a number. But now it's no longer the case because it's just block diagonal. So there is a possibility that you act on this state and it gives you another state. But the other state is still within the block. It doesn't take you to a new state of a different principal quantum number. So you can see this is eigen in the sense that the principal quantum number doesn't change, but the secondary quantum number can change. And then this matrix or this quantity is supposed to replace the eigenvalue. Previously, when there is no alpha beta index, then this is simply the eigenvalue because this summation doesn't make sense when there's no degeneracy. But when there's degeneracy, it becomes a matrix, which is a matrix that's specifically defined in the n subspace, and the matrix is labeled by alpha and beta index. So this matrix describe, if I apply this Hamiltonian to the state in this subspace, how do I need to rewrite this state as a combination of all the bases in this alpha, labeled by the same principal quantum number n, basically in the subspace. Okay, so this is called the effective Hamiltonian for the nth degenerate subspace, and for each degenerate subspace, for each block, there is such a block effective Hamiltonian. And this, I'm not saying that this is the result. This is our goal. Our goal is to infer what is this guy and what are these new bases. So of course, when lambda equals 0, when there's no perturbation, then this effective Hamiltonian should fall back to the original Hamiltonian, which means in the original Hamiltonian, what happens is that everything is already diagonal. So that's why it looks like this looks like En, which is the eigenvalue, which are all the same within this unlabeled subspace, and then multiplied by delta alpha beta, which means it's a diagonal matrix with a matrix element En everywhere. So that's what we know in the unperturbed limit for this guy. So now we can use perturbation theory to calculate its corrections. So that's basically the idea. So in order to do that, again, we need to go through this Hermann-Feynman theorem. And I want to mention that we want to start from this equation, and then we can derive the Hermann-Feynman theorem. So starting from this equation, this is like an assumption, assuming that after you apply, after perturbation, the solution, the block diagonal solution will have such a structure. You can also do a Hermitian conjugate on both sides and convert cat to bra, and also convert every matrix element to its complex conjugate followed by transpose, something like that. So you can write everything down like that. And then in writing that, I have secretly used certain hermiticity of this block diagonal matrix, but that's not so important. The idea is that now you take this eigen, so the generalized kind of eigen equation, although it's no longer eigen, you can take this formula and then try to compute this. On this side, you apply partial lambda h, and then should I explain where it comes from? I'm going to apply partial lambda to both hand sides of this equation. So then I will have h being partial, and then this state being partial, and this state being partial, and this e being partial, right? Altogether 4 terms. And these 4 terms correspond to term number 1, number 2, number 3, number 4, these 4 terms. This term is actually moving from the other side of the equation to here. And then you can see the partial applies to h, to this state, and then to this some alpha state, and also to this e, basically. And then you need to do some simplification, and you also need to inner product with another m gamma in order to arrive at this final answer. And this answer, you can see this structure is really similar to the Hermann-Feynman theorem, which is a formula that connects something on the left-hand side. So based on this formula, you can obtain these 2 conclusions. When m equals n, then the second term vanishes, and then the first term tells you something that connects the energy derivative of this. This is no longer a single energy eigenvalue, but you should say this is like an effective Hamiltonian. So this effective Hamiltonian has a lambda derivative, and how do I connect that to something that doesn't contain the lambda derivative? Which is how do I connect that to, for example, this perturbation that apply to the system, right? So this allows you to reduce the number of the orders of lambda derivatives on the effective Hamiltonian. And then when m not equal to n, so when m and n they are not the same, the principal quantum number are not the same. When the principal quantum number are not the same, we are guaranteed that these 2 energies are different. Although there are degeneracy in the system, but previously we say that we have used principal quantum number to label all the different energy levels, and all those states that is of the same energy will be labeled by the secondary quantum number. So as long as the principal quantum number are different, we are free, or we are safe to basically say that En and Em is not going to be the same. So as long as it's not going to be the same, you can basically divide it on the denominator, and then when m doesn't equal to n, the first term vanishes, then we have something that is related to the state correction or state derivative. So this formula tells us if I have a state which is labeled by principal quantum number n and secondary quantum number beta, and the state will change under perturbation if you apply the perturbation, the rate of change of that state and then project it to another basis will be related by this formula, which doesn't contain derivative of lambda. So this second Hermann-Feynman theorem allows us to compute the derivative of a state, converts that derivative into something that doesn't contain the derivative. So all these ideas are still the same, that this Hermann-Feynman theorem allows us to reduce the orders of derivative with respect to lambda by one order. But then we know that in order to do the state and energy correction, all we need to compute is, for example, how to correct the effective Hamiltonian and how to correct the state. It all relies on how to calculate all these higher order derivative of the effective Hamiltonian as well as the state basis. And then these can all be done, and then the calculation exactly follows what we described previously. You can see that the result is also look very similar. The only difference is that now every state is not only labeled by the principal quantum number, but also by the degenerate, like a secondary quantum number. But you only need to be very careful to go through this derivation and keep track of things. You will be able to show that this is the result. And if you want to convince yourself, you can consider the limit where there's no degeneracy, meaning that you can remove all the secondary quantum number. You will see that the formula exactly fall back to the non-degenerate perturbation. So that gives you some confidence that I'm not just bullshitting. I'm actually talking about something that is reasonable. So, okay, so this is the final result. When you plug in these derivatives into the Taylor expansion formula, one can obtain how does this, for example, effective Hamiltonian being corrected. You can see that when lambda is 0 without any perturbation, the effective Hamiltonian within the nth block is a diagonal Hamiltonian. This is because H0 was originally diagonal, which is diagonal means that its dependence on beta and alpha is given by this delta alpha beta. And then the corresponding eigenvalue are all the same within this n block. Within this same n block, it's all E of n. But you can see after applying the perturbation, there will be term adding to that, which make it non-diagonal. For example, there will be term like Vn alpha, Vn beta, which is the perturbation within that block. That guy will just be added to this E. So that idea is basically the same. The first order correction is always just simply add this diagonal block perturbation to this, into this diagonal block. But there will also be second order corrections. Second order correction correspond to if you try to correct, you try to understand what is the correction from beta for this alpha beta element. So you should read this alpha beta element as a matrix element that connects the beta state to the alpha state within the principal component block labeled by n. So beta and alpha are two states within this n block. And then in order to do that, you need to first start from the n beta state and go to something like m gamma. You can go out of the block in order. So beta and alpha are two brothers in a home. So in order to do their correction, they first need to visit a friend that is outside their home. And then when they come back, they can mix with each other. So you can start from n beta to some m gamma and back to n alpha. So this describes, after the perturbation, how much connection you can build between alpha and beta by going through a third state, which is not even within the degenerate block. And because this third state, this intermediate state, is doomed to be some state that is outside this degenerate block, so we never have the concern that this energy denominator will diverge. This energy denominator will always be, never concern the denominator will vanish. So the denominator will always be a finite number because the principal quantum number labels different energies already. Okay, so that's the idea. And then the same applies to the state correction, that if you start from an n alpha state, you have the chance to be mixed with the m beta state. And then the amount of mixing will be proportional to the connection, to the strengths that this perturbation can connect you from n alpha to m beta. Of course, it again depends on the energy denominator to adjust the coefficient. Okay, so these are the result of degenerate perturbation, and with that, basically one can form a so-called effective Hamiltonian. Effective Hamiltonian again is a matrix or is an operator, and this operator is given by cat state, and this matrix element, this should be considered as the matrix element of the effective Hamiltonian, and then bra state, basically. So this cat and bra will be taken from the state correction. The state correction just gives you the cat state correction, but the bra state is just flip everything around. And then this this effective Hamiltonian matrix element will be given by this. So if you put all these together, one can write down an effective Hamiltonian that acts within the n subspace. So the full Hamiltonian will just be the direct sum of all the effective Hamiltonian. By that I mean that all I have been talking so far, I have tried to explain this process. How do we come from this block, which have this off-diagonal matrix element? Then we have end up with a situation that that allows us to block diagonalize the matrix, and then we obtain the effective Hamiltonian within each block. For example, this is n equals 1, this is n equals 2, and then within n equals 1, there'll be state labeled by alpha and beta, and so on, like that. So this allows us to somehow block diagonalize. How do I know I block diagonalize? That is this assumption. Assuming I can block diagonalize the new Hamiltonian such that the new Hamiltonian, when it acts on the state, I'm allowed to mix the state within the block, but I'm not allowed to mix the states between the block, meaning that I'm not allowed to change the principal quantum number. So this equation means that this Hamiltonian has been block diagonalized, that there is no longer any mixing between different blocks. So, but within the block, there can still be mixing between alpha and beta state, which is described by effective Hamiltonian. So this allows us to clear up all the off-diagonal blocks matrix elements, and then if you just keep applying this, now you can zoom in each block and try to see within that block whether there are still degeneracies or not. And then if there's no degeneracy, you apply the non-degenerate perturbation theory. If there's still degeneracy, you do this exercise again. So, so by iteratively applying this degenerate perturbation formalism, one can basically eventually diagonalize the full Hamiltonian. But this math is not important because nowadays you can look up Wikipedia, you can use PyTorch, machine automatically calculate all this. I think the spirit or the philosophy is more important. The philosophy of divide and conquer is the most important lesson that we learn. And then the divide and conquer is based on the energy scales. You need to first divide your state into subspace of similar energy. And then you try to you try to decouple, basically, the two subspace. So that's what we can see here. Try to decouple the two subspace and focus on each subspace and try to do further research. That's the idea. So when we do physics research, it's also the idea you can't start from the very fundamental level and quarks and leptons and try to explain how, for example, intelligence emerge in human brain, right? So that's completely two physical process at two different levels. You need to first decouple these energies and then study the physics at different energy scales, and then keep splitting it, and then that leads to that's why physics is such a huge subject, right? There's so many different parts of physics trying to deal with different energy scales, and that all comes from this idea that you can indeed, in quantum mechanics, you can divide and conquer. If two energy scales are very different, meaning that for example, if two blocks, they are separated by very high let's say, if you have two principal quantum numbers which correspond to completely different, very different energy scale, then you can see this denominator will be very small, no matter in energy, in this effective Hamiltonian correction or in this basis state correction. All these denominators are controlled by the energy splitting. So if you have energy process of different energy, the energy difference is large, then the perturbation theory is actually very good. Large energy scale separation means that a good isolation of the physics. So, so that's why, that's the fundamental reason that we can use this idea to study physics in different energy scales. And I don't want to talk about time dependent for today, and so that's it. Thank you for your attention.